Good evening and welcome to Tinkering with Edkelar. In the previous 2 episodes of the series, I disassembled, cleaned and started to poke around in a Fluke 5100B calibrator. Now, the conclusion. Up next for recapping, the isolation board. It takes the digital control bus on one side and transfers data and address bits over to the instrument bus. This is done with a clock and a shift register, so 2 transformers take care of that. The addressed instrument card takes the bits and sends back an ECK signal for the CPU. This is the 3rd transformer. And the 4th? That one carries the overload line from the instrument bus back to the digital one. It's a weird combination. ECK is basically mapped to the interrupt line on the CPU, while the overload one is mapped to the MSB on the data bus. Speaking of controller, here we go. An 8080 CPU complete with 2 ROMs and 2 RAMs. RAM? Oh, it seems that my 5100B unit was well maintained. This controller is actually from a 5101B. It's the storage model. Not sure what I can do with that without the tape drive, but hey, if it's there, I'll try to use it. The front panel cleans up reasonably well, but the outer frame is scuffed up and the red plastic for the LED displays has a matte finish that flakes off in large parts. I think it's time for some paint action. Not perfect, but okay. I need to replace the model number eventually. Mounting the front panel to the display board again, not to forget the double shielding tins. After putting in the ranging board, the front panel and the controller, I power up the lot and see if I have signs of life. And indeed, I get greeted with the firmware version and an ERR6 error code, which means module not found. Indeed. After that success, I quickly add all the boards that are required for any output. Low range DC seems to be the easiest. The digital analog converter board, analog control, amplifier and oscillator should do the trick. Yes, I'd call that a success. At the very basic level, this device is a high-precision regulated supply. It is not geared towards power, however. That is, the output is only ever going to be a few watts tops. Just enough to drive a connected meter, no practical load. So in current mode, it is expected to have hardly any voltage, and in voltage mode, it is expected to have hardly any current. All the different relays on the PCB make for a whole lot of different configurations of the circuitry. Different parts are put into play or removed based on the operation mode and range requested. The low range DC, all below 20 volts, which is the point where my unit is supposed to fail, is done with this configuration. The numeric value that is requested as an output is set from the digital analog converter as a reference voltage, the output of which goes through the power amplifier to the output and back via the sensing lines and a divider network for the control loop. Voltages below 2 volts have a separate precision divider so that the regulated control voltage is still in the 0 to 10 volt range. Note that this can't use the sense lines because their feedback would be off by orders of magnitude. AC voltage is created from the oscillator PCB, amplified by the same power amplifier. The gain and thus absolute output value is controlled via the analog control feedback loop again, but this time there's an integrator put into play to convert the output AC to DC first. The oscillator can provide a discrete set of frequencies only, but it does provide a pretty nice sine wave output. For higher voltages, there's the extended high voltage PCB that acts as a step-up transformer. Now, when asking for 20 to 1100 volt AC, the high voltage board uses the big transformer instead of the small toroidal one. It has two primary coils to aid in different ranges again, and also a pretty standard rectifier and filter circuit for making DC output. The rest is the same as for the low-range AC configuration. Now to the currents. For currents under 200 mA, this circuit looks about the same as for voltage. But the control feedback is taken from the current shunt resistors rather than the sense lines. Note that the provided iGuard socket is for shielding low amperage but high frequency currents and will mimic the driving voltage. iGuard should thus never be shorted to any other binding posts, which it was on my unit. Currents above 200 mA up to 2 amps are using a different amplifier section in the power amplifier board, but everything else is the same. All current modes monitor the voltage that is output from the amplifier board on the control PCB, and if that voltage rises above 2 volts, it triggers the overload condition, which will turn off the analog section immediately and also send an overload signal to the controller, which then in turn shows the user and turns off the output properly as well. And finally, resistor values. I was hoping to have arbitrary values available by some voltage and current manipulation game, but the solution is much more primitive. The ranging board can configure the divider networks into decade values, so it provides an actual, real resistor, but only the one value of every decade. 1, 10, 100, and so on, up to 10 megaohms. Meh. Should still be good enough to calibrate most meters though. It even can provide 4-wire connections via the sense connectors. Now, I thought I had a demo recorded, but it seems my camera ran out of battery at the wrong time. Anyhow, whenever I entered either a DC voltage of 20 volts or higher, or any AC voltage, the unit immediately showed OL, overload, in the display and shut down the output again. Time for some troubleshooting. This here is the analog control board and the only place that drives the overload signal for the controller. I spent hours following the signals all over to see what causes the condition, which should only relate to current, not voltage delivery. I found that one of these drivers, an open collector TTL hex inverter, didn't quite invert all of its inputs. So to rule that one out, I piggybacked a regular inverter on top until I got the open collector one. These things run between -15 and -20 volts, so when they pull low, there are -20 volts pulling. That way they can drive field effect transistors directly, but a regular chip, that is a not open collector one, would certainly cause havoc with those. So I only bridged the one output that I wanted to validate, and it worked. Replacement chip ordered, but the overload problem still remained. And shortly before giving up, I saw that the overload signal is also picked up by the amplifier board. Why? Turns out that this little section on the lower right edge is connected to the overload line and can also drive it low. Yikes! So clearly the overload was not current related, but the amplifier was getting too close to one of its rails. The plot thickens. Now the various supply voltages and different grounds all over make the control loop rather complicated. This section here, for example, takes an analog voltage from one ground and transfers it over to a different ground. How? By continuously charging one capacitor with the input voltage and then swapping that capacitor over with the CMOS switch. Since this happens at several kilohertz, one of the two capacitors will get charged on the input side and the other one discharged into a buffer op-amp on the other side. But alas, all was well here. My next suspect was the strange buffer integrator stage on top. I asked around in my usual places, since I'm still nowhere near as proficient with op-amps and analog stages as I like, but I was right. The two transistor stages should act as a current source with a mirrored behavior. The trimmer on top is to equalize the two legs. Now, why then does my meter show almost 1.3 volts difference between the two sides? I expected a broken transistor or such, since I could adjust the trimmer all I wanted and nothing changed. But when I checked what range the trimmer had, it turns out that the trimmer was broken. Ha! Another déjà vu. I still have a spare one of these buggers from the Tech Curve Tracer repair, so it's easy enough to replace. Bam! I got AC and DC above 20 volts. Woohoo! Now to do all the alignment and adjustments. Sheesh, here's the problem again. All my meters are so accurate, and here I need to dial in voltages, currents and resistors to crazy accurate values. For example, the internal reference voltages plus minus 10 volts call for a 50 microvolt tolerance. That is 10.0005 volts nominal, so anywhere between 10.00045 and 10.00055 volts. Anyhow, I still used my regular gear to calibrate it as good as I could, so as to see if the ranges work out. This is when I found out that the plus 10 volt reference was a bit out. Negative 10 volt I could get to 10.0000 according to my most precise meter, but positive was stuck at 10.002-ish. So, surgery again. I replaced these two 10 ohm resistors with two 22 ohm ones, so the overall range of the adjustment trimmer will be slightly higher. That way I could get both of the voltage references to exact 10 volt. And the wideband output also checks out. It had quite a bit of wobble on it, but after fitting the shields again, quite stable. The IEEE card is next. It has a main part and a piggyback board with some additional logic, cleaning all the contacts and adding it to the system. And now for a quick IEEE test, sending over a few commands. The instrument does detect the access and switches to remote mode. And it also performs the requested operations. Sweet! The case feet were missing, so I used OpenSCAD again. Well, this is it. I now have a calibrator that needs some calibration. I'm still looking for a decent rental here. Bringing that thing to a standard lab and have it formally calibrated will certainly cost more than a rented meter. I checked, they charge per calibration point and there are quite a few in here. So, this is it for now. I hope you enjoyed this rather special project. See you next time! And it also has the power lines for the other section embedded. Darn it. These are also clamping down on a 1.0033 ohm resistor and provide a heat singing for they provide heat singing. What did I type here? La 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 la. It is so hot, it's so hot.